Hi there, this is part 2 of my introductory series on Astron, in which we will discuss the moving parts. It could also be called what Astron looks like from the inside, as we will be dealing with the things that exist and move around inside the infrastructure created by an Astron network. First, let's get some basic vocabulary down. The things that exist inside an Astron network are called participants. They can send messages to channels and they can subscribe to channels. Channels are 46-bit IDs. They do not exist as actual objects, they are just numbers used as addresses for routing. When a message gets sent to a channel, it will be forwarded to all participants that have subscribed to that channel. Messages are the data packets sent around between participants in a network. They consist of a to-channel, a from-channel, a message type, and a payload. The to-channel is simply the channel that the message is sent to. The from channel is usually a channel that the sending participant subscribes to, so that it can receive replies to the message. Server-side participants, however, can also substitute any other channel for the from channel, akin to writing someone else's address on an envelope as the return address to facilitate an exchange between that person and the addressee. A message type is simply a 16-bit number referring to one of the message types defined in the Astron protocol. Currently there are just above 100 of those. The payload is the actual data that is exchanged. Its types and meanings are defined by the message type. Let me summarize this in a pretty picture. There are participants, they subscribe to channels, they send messages to channels which then get forwarded to the participants who have subscribed to that channel, or they can create messages in the name of other participants to facilitate an exchange between those participants. As channels are usually subscribed to by only one participant each, we can also consider them simply to be properties of those participants and are left with the very simple picture of a bunch of participants who are passing messages to each other. Now that we know the basics of messaging, let's look into what kinds of participants there are. The most common kind is the distributed object, which is created from a distributed class. Distributed classes are defined in a DC file, and they reference views, which are Python objects that will exist in server or client processes, and that determine the behavior of the distributed object for which they act as proxies. Distributed classes define methods, which are annotated with keywords that define the routing and other behavior of messages concerning those methods. For instance, a method may be turned into an attribute by using one of the keywords that make the network's database store the payload of messages created by such a method call in a field. Here we've got a snippet from a DC file in which I define a distributed class named distributed_avatar. The first line states that Python classes corresponding to this distributed class can be found in the module Simple Example, and that there are 3 such views, namely distributed avatar, distributed avatar AI, and distributed avatar OV, which stands for owner view. These classes will have 2 methods, namely setXYZH and indicate_intent. setXYZH is actually a field because it has the keyword required, which means that when a distributed avatar object is created in the network, it is required to have a field named setXYZH. Indicate_intent has no such keyword, which means that it's purely a method. setXYZH also has the keyword broadcast, which means that every participant who can see this distributed object will get updates when the field is modified. Seeing hereby refers to a concept called interest, which I'll explain later in this talk. Indicate_intent has the keyword ownSend, which means that only the client that is the owner of this object may invoke this method. It also has the keyword AI receive, which means that messages created by calling this method will be routed to the AI process controlling this object. The definition of arguments for these methods determines how data is packaged into message payloads. For instance, when calling indicate_intent, its floating point arguments will be multiplied by 10, cast into a 16-bit integer, sent over the network, and on the other side divided by 10 again, yielding again a floating point value. Once created, all distributed objects have an ID which is a 32-bit integer and which also acts as a channel that the object is subscribing to. Currently, they can be assigned by the application developer, but this is a functionality that will probably vanish soon. Semi-random numbers, the way to go, should be treated as random numbers, but they are actually created simply by accounting upwards from a lower limit. Distributed objects also have zones, which act as containers for child objects. They are 32-bit numbers, and like channels, they only exist by being used. The tree that distributed objects create by using this scheme is called the visibility tree. Distributed objects also have a location, which means that they reside in a zone of their parent object. Having a parent object is currently optional, and objects that do not have parents form the root of their own visibility tree. Currently, there's also a special type of distributed object named the Distributed Object Global, or for short DOG. These objects always have a predetermined ID defined by the application developer. They have neither parents nor zones and thus are not part of the visibility tree, and they are already slated to be deprecated. Usually there's one AI process named the UberDoc that manages these distributed object globals. Let's summarize again with a picture. So far there are messages and distributed objects. Messages are defined by the channel that they are sent from and to, by their type, and by the fields they carry their data in. Distributed objects have an ID, they have a location in which they reside, and they have zones in which other objects can reside. They have methods that represent underlying messages, and the payload of these messages and their routing behavior is defined by the signature and keywords of those methods. Let's take a quick closer look at locations. They are channels that refer to zones of distributed objects, and their IDs are created simply by putting the distributed object ID in front of the zone ID. There is also a bunch of other channels in use in an active Astron network, namely those channels for distributed objects, repositories, and certain roles of the Astron daemon process, namely the client agent and the state server, which I will discuss in the next video. There is also a list of reserved channels. The lesson to be learned here is that your object IDs should be numbers between 1000 and 4.2 billion. Now let's talk about what makes server and client processes tick. Repositories are objects in a client or server process that handle the network connection to an Astron network. There are two kinds of them, Astron internal repositories and Astron client repositories. Internal repositories are used by processes on the server side, and they are not subject to security checks. They can send any kind of message that they want to. As Astron client repositories are used by clients, they are considered inherently untrustworthy and as such are subject to security checks. Any kind of transgression detected by these checks is answered with an immediate termination of the network connection. Nobody likes a cheater. Astron internal repositories choose their own channel at which they can be reached, while Astron client repositories get their channels assigned when a connection is made. The point of having these repositories is that they manage a pool of views on distributed objects, which are Python objects that implement the behavior of the underlying distributed object, by creating or reacting to messages and through their Python API. They inherit the class distributed object, which in the Panda 3D-based implementation of repositories also inherits direct object to tie everything together with Panda 3D. They also keep a reference to the repository in which they reside, namely self-AIR or self-CR, depending on the kind of repositories. This will probably soon get streamlined into self-repo. There are four kinds of views: the default view, the AI view, the owner view, and the UberDoc. Default views are used by everybody and do not confer any special privileges. AI views are solely used by server-side repositories. Owner views are used by whoever is assigned as the owner. Ownership is a mechanism to assign special privileges on the game mechanics side of things. It can only be conferred to one client at a time. And last but not least, the soon-to-be deprecated UberDoc view is used to manage UberDocs. Note that when an Astron internal repository is created, it has to choose whether to use AI or UD views. And at last, let's have a closer look at interest. Interest defines what a client can see, namely what objects it gets information about. They are usually set by AIs, because if clients were allowed to set interests for themselves, they could elicit more information from the server than they should have. Interests are set in locations, and they cause messages to be created to the client having its interest if a distributed object enters or leaves that location, or publicly readable fields of a distributed object in that location change. As a message payload, they consist of an interest ID and the ID of a context in which that interest is set. The context mechanism is provided to make managing interests easier. For my grand finale, I shall again summarize. There are distributed objects, which reside in locations, which are zones in their parent objects. By calling methods in views, messages are sent over the network and routed according to the keywords provided in the DC file. By default, the visibility tree is invisible to new clients. Server-side processes set interest in the name of the clients, slowly growing their awareness of the visibility tree. Clients then will get updates about the objects in the locations that they are interested in. I'd like to wrap things up by talking about some best practices when working with Astron. First of all, consider the asynchronous nature of networking and possibly resulting race conditions. While view methods look like standard Python to the developer, they can't react to the replies to messages that they have sent. As such, return values, if provided, only reflect the local proxy state of a distributed object. This also means that views in different processes may try to interact with the same object. While doing so, there is no locking of the object, so your views will have to work in a way that makes your calls atomic, or you have to use other ways to deal with asynchronous access. Usually, luckily, this is not too difficult to do. You should also restrict a client's access to information or control as tightly as possible. Every bit of control or information that the client has access to when he shouldn't is a cheating exploit waiting to happen. While Astron provides access controls, it does not provide value control. Any value that a client sends should be subject to sanity checks to file further exploits. That's it for today. This has been the second part of currently 3 planned parts of my introductory series to Astron, soon to be followed by a further series on building and deploying Astron, on example code, and on advanced techniques that can be built upon distributed objects with Astron. Here are again a whole bunch of ways to reach me. Thank you for watching and hope to see you next time.